Whoa. Okay. Hi, everybody. Can everyone hear me today? No? Okay. I think we're trying to figure out the miking back there. Oh. Sorry about that. Okay, I'll be giving a lecture today. Professor Boyd is off in Paris, France, and he didn't make it back in time to give this class. So I'll sub in for this short lecture today, and we'll have a quiz at 9:40, which hopefully you'll find easy. Okay, so last week's homework emphasized Bode plots so much that I suspect not many people have had a chance to focus on the feedback chapters we've been covering. So last time we began the dynamic analysis of feedback, and I want to begin with a quick review of that before we move on to today's subject, which is integral control. Okay? So just to recap from last time, in the dynamic case, in this feedback control configuration, our controller and plants are now dynamic. They're not just simple gains as they were in the static case. Okay, and let's recall the goals of feedback control. The basic idea is to make the output track the input as closely as we can. Okay, and we want to do this despite variations in the plant. Okay, and also despite input and output disturbances to the plant. Okay, so in the course of the analysis, we arrived at two definitions. The first of which was the loop transfer function, which was the dynamic case generalization of the loop gain for the static case. And we also defined the sensitivity transfer function given by 1/1 plus PC. Okay? And so when we went about finding closed loop transfer functions and for the closed loop system, okay, we found some quite neat results. Okay, the first of which, for instance, was the closed loop transfer function from the input to the output, which we called T of S, okay, given by PC over 1 plus PC. And with a little work, you show that that's equal to 1 minus the sensitivity. Okay. Similarly, the closed loop transfer function, this is what this abbreviation means, from input to the error is given exactly by the sensitivity. And the closed loop transfer function from the input disturbance to the error is given by the product of the sensitivity with the plant transfer function and the minus sign. And lastly, the closed loop transfer function from output disturbance to the error is given by the negative of the sensitivity. Okay? From all these transfer functions, okay, and from the consideration that the fractional change in the closed loop gain is a fraction S of the fractional variations in the plant gain at some frequency, okay? From this, and together with these results, we realized that the obvious thing to do to get the benefits of feedback is to make the sensitivity as small as we can. That's equivalent to making the loop transfer function as big as we can. Okay? So, oh, sorry. Okay. So I hope that's clear to everybody at this point. The only problem that we have to deal with, okay, is actually a very serious one, which is the following. When we add the controller and we make the gain of the controller large enough to meet our purposes, okay, we have the risk of making the system go unstable. Oh, okay, nobody can hear me out there in the back? Okay. Hopefully they can mic me up a little bit louder. Can you guys hear me better? Yeah? Okay. Let me know if I should speak louder. Okay, so the idea was that in the closed loop system, you could have unstable poles. if you don't design your controller right. And let's see why that happens. So if I look at the loop transfer function, okay, which is the product of the plant and controller transfer functions, and I write it as the ratio of two polynomials that I call num and den, okay, and I plug this expression into the transfer function, I get at the end the following rational function for the closed loop transfer function, okay, where the denominator is given by the sum of the loop transfer function's numerator and denominator, okay? So this polynomial here could have poles on the right-hand plane, even when the numerator and denominator have roots. Even though when this denominator has roots only on the right-hand plane, left-hand plane, excuse me. Okay, sorry about that. I didn't say it as well as I wanted. So the big question now is to find a way of knowing whether the roots of the closed loop transfer function denominator are all in the left-hand plane. Okay. And this brings us to where we left off last time in the lecture notes, lecture 12. Okay. And we're going to discuss now methods for checking the stability of a system. So in general, if I give you a transfer function b over a, okay, the answer to whether the system is stable is simply whether or not the roots of the denominator are in the left-hand plane. Correct? We say a polynomial a is Hurwitz, okay, if the roots are all on this left-hand plane. Okay? I don't know where the name comes from myself. So if I were to ask you, how do we know if the polynomial has roots on the left-hand plane? Well, there's a few things you can do. If I give you the polynomial in the factor form, then the answer is obvious. All you have to do is look at the roots and tell me whether any of them has a real part that is greater than 0. If that is the case, then you know your system cannot possibly be stable. Okay? Okay. But here's a more complicated case where possibly I give you instead the polynomial describing the denominator. Okay? For instance, I could give you in MATLAB, I could pass the vector an minus 1, an minus 2, and so forth, all the way to a0. Okay? And then I say, tell me about the stability of a system whose denominator is given by this polynomial. Okay? Okay. This is also very important in the context of control, because now the controller parameters will affect these coefficients here. Okay? So you'd like to know for what parameters your polynomial a has roots on the left-hand plane. Okay? So fortunately, there's a lot we can do. The problem is, if you recall, that for polynomials of order above 4, there's really no formula for determining the roots. Okay? For the third order polynomial, there is an analytical formula, but it's absolutely complicated. And no one in their right mind would go about plugging in the numbers to get the roots that way. Okay? Okay. But here's the punchline. In 1870, Routh showed that actually you can determine whether the roots are in the left-hand plane without determining exactly what the roots are. If the polynomial coefficients satisfy certain inequalities, you can tell whether the system is the polynomial will have the roots in the desired place or not. Okay? So, okay. So, a few years back, when computers weren't around, this method was very useful, okay, because you just had to check inequalities, okay. Nowadays, with MATLAB, you can just type roots, and you get the roots numerically, no problem. But this method is still interesting because in the context of control, the polynomial coefficients involve the controller parameters, like the overall gain, of the controller and other parameters that you'll see, for instance, in today's lecture. So the interesting question now is, for what range of controller parameters will my system be stable? And using these inequalities, we can determine those ranges very easily. Is everybody with me? Okay. Okay, so let's look at that right now. Okay. 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 The first thing here that Boyd states is that the highest order coefficient can always be set to 1. Okay? Because you can simply divide the whole polynomial by a sub n, and that won't change the roots of the polynomial. Okay? Okay. Okay, so this is the a of s we're going to be looking at here, of this form. And here's an interesting result. There is a necessary condition for the polynomial a to be Hurwitz. Okay? And that condition is that all the coefficients be greater than 0. Okay? That's a necessary but not sufficient condition, meaning that if I give you a polynomial whose coefficients are all positive, that doesn't guarantee that the roots are going to be on the left-hand plane. Okay? Doesn't guarantee that. It does for first and second order systems, as we'll see, but not for higher order systems. Okay? To see why it's a necessary condition, well, this is what we do. If I give you the polynomial in a factored form, okay, like this, okay, here I've put the complex roots in a real factored form. Okay, so there's really 2 roots inside of this second order polynomial. Okay, if I tell you that the system is stable, then that means the p sub i's are all less than 0, okay, and the sigma sub i's are all less than 0. That means this here is greater than 0, this here is greater than 0, and both of these are of course greater than 0. When you multiply polynomials whose coefficients are positive, okay, the resulting polynomial will always have positive coefficients. Okay? So the conclusion is a stable system, okay, has all coefficients greater than 0. Okay? The right way to say is when they all have the same sign. The reason why we say positive greater than 0 is because by dividing by n sub n, we've made one of the coefficients exactly 1. So that restricts the sign to be the positive sign. Okay? Okay. So here's an example of how the converse is not true. This polynomial here, with coefficients that are strictly positive, turns out to have roots on the right-hand plane. Okay? Like this. Okay. So here are the Hurwitz conditions, these inequalities that I mentioned a few minutes ago. Okay? There is a method for deriving these inequalities, and I know them as Routh's method, okay, which we won't go into in this class. But if you're interested, if you move into control courses like EE102, you will learn this method, and it will allow you to derive the relevant inequalities for much higher order systems. Okay? Here we're just going to list the inequalities for polynomials up to degree 4. And the reason is that we probably won't care for higher order systems in our course. Okay? So let's visit some of these inequalities. For degree 1, the answer is obvious. The root of the polynomial is at minus a sub 0, right? And therefore, the condition that the polynomial be stable is simply that the coefficient be positive. So that's easy, right? For degree 2, the condition is that both coefficients be positive. Okay? So in this case, the positivity constraint is not only necessary, but it's also sufficient. Okay? If you want to prove this to yourself, one way to do it is look at the roots that you can get from the quadratic formula. Okay? And the roots are given by a1 plus minus A1 squared minus 4 A naught over 2. Okay? So if you reason it out, you realize that if A1 only if and only if A1 and A naught are positive, you will find that the real parts of these roots, of both the roots, is negative. Okay? It's a simple exercise. It used to be a homework problem. Okay? Okay. And then let's move on to degree 3. Okay? Here we have the first non-obvious inequality. We have the obvious necessary conditions that the coefficients be positive, and we have this additional one. Okay? I'm not going to tell you where that comes from. My answer is it comes from Routh's method, and I hope you're okay with that. Okay. We'll see an example of this in the next page. For degree 4, again we have the necessary conditions and an extra set of inequalities, okay, which are a little bit more complicated, right? Oh, excuse me. Okay. So I don't have much to say. I don't have any intuitive understanding for why the inequalities are the way they are, okay? And I don't know that Routh's method gives them to you. Okay, so these are the inequalities for polynomials up to degree 4. Okay? Okay. Okay. So for degree greater than 5, even these conditions are very complicated, Boyd tells us. Okay? And but Routh's method, sure enough, will give them to you if you look for them. And once again, the inequalities consist of sums and products of the coefficients. Okay? Okay, let's move to our favorite example, okay, for an application, okay? And it's the plate heating system we've been looking at for 2 lectures now, I think. And that heating system had a transfer function with 3 poles. Remember this? There was one at minus 10, one at minus 5, and one at minus 3. Okay? These are the roots of A of S, alpha of S, which was that heater transfer function, okay, from input power to output temperature. Okay? So if you work out what the denominator A for the closed loop system is going to be, it looks like this. Okay? It's still a 3rd order polynomial, okay, but now it has the controller gain here that we talked about last time in it. So this K is responsible for moving the roots. Okay? So let's find what the conditions on K are such that the closed loop system will be stable. In other words, such that this polynomial A of S is going to be Hurwitz. Okay? So we plug in our inequalities here for 3rd order. Okay? And right away, you will find this condition for the gain of the controller. Okay? So it basically says if the controller gain ranges from minus 1 to 10, you'll be stable. But anywhere outside that range, you'll be unstable. Okay? If you remember the numerical example that we ended up with last time, Professor Boyd was asking, what happens if I change the gain? And then he found that, I think he had a gain of 15 in the last one. And sure enough, for that case, the roots were in the right-hand plane and the system was unstable. Okay? So here's a way to see all of this. And it's by doing a root locus, okay, which shows how the poles move as you change the gain. Okay? Here I've shown how the roots move for positive gains. Okay? So these are the roots of the denominator of the plant transfer function. Okay? And so if you look at the loop gain, PC, then you would find that these are the poles, of course. And so when you close the loop and you look at how the poles have moved, okay, as a function of k, this is what you get. It's kind of interesting. Okay? When you start from k equals 0, you're exactly here. And then as you move, this pole starts moving off to negative infinity. So that's kind of a nice thing, right? But these other ones, look what they do. It's kind of funny. They come in, they crash, and then they crash, and then they move, they split, like this. And sure enough, as you increase the gain, look, they move towards the right-hand plane. And they cross the imaginary line exactly at k equals 10. So for k greater than 10, where your complex poles, these complex poles will be right in the right-hand plane, you've gone unstable. And so it's obvious that you're in trouble. Okay? So just out of curiosity, let's ask, what happens now when I make the k negative? The controller gain negative. How do the poles move in that case? And you don't need to know this. Okay, this is the subject of EE105, and it's very interesting when you, if you're into this kind of thing. And what happens for the case of negative gain is this. This pole moves to the right, and it's eventually the pole that crosses the right-hand plane, the imaginary line, and causes the instability for gains below negative 1. Okay? And these two poles, they move closer to each other like this, and then they split, and they go off this way. Okay? So, like I said, you don't need to know this, but it's so much fun I couldn't keep from mentioning it. Okay. Okay, so let's summarize the contents of this chapter on dynamic analysis of feedback. Okay. So the first thing was that we generalized these ideas of forward gain and feedback gain to transfer functions. Okay. So now every term looks the same except it's a function of s. That's the first statement. Okay. Then we mentioned that we run the risk of making the system unstable. Okay. A notion that we didn't have for the static case. Okay. And finally, the note that the stability requirement often limits the amount of feedback that can be used. Okay. I have to say that that's not always true. There are systems for which, if you increase the gain ad infinitum, you won't go unstable. Okay. Let me just give you an example. If I have a simple pole in the transfer function, okay, in the plant transfer function, and I use proportional control, okay, then it turns out this pole moves this way as I increase the gain. So I can increase the gain as much as I want, and I won't go unstable. Now the truth of the matter is that every real system, okay, I don't know every, but most physical systems tend to have poles, many poles. Mechanical systems are notorious for having poles really, really close to the imaginary line. So when you apply feedback, it's almost inevitable that you will have poles moving onto the right-hand plane. Okay, but I just thought I'd mention that in case you thought, increasing the gains of your controller and so forth will always lead you to instability. Okay. All right, so let's move on to the next class, the next lecture, which is integral action. Okay. We have some more handouts of that lecture here, I think. Oops, they're gone. So everybody has a copy? Okay. Integral action. Okay. The first thing to say is that what you'll see today is what Boyd would say, it's widely used in practice. And I heard him once say that integral control of the kind we'll do here, you will find in 70% of control systems that you find in industry, like process industries, like paper milling and all sorts of things I don't know about. But here I think is where he would do his little snippet of history and tell you that 70% of feedback control in reality is done this way. Okay, so it's very, very, very important. Okay, and this is known as PI control for reasons you'll see in a second. So we go back to our friend, the feedback system. Okay, we stick again to the feedback control configuration. Okay, where our goal is to make the output track the input, despite these variations and despite input disturbances and despite output disturbances at the plant. Okay, so okay, whoa, I wish I had brought a clean set of notes. Okay, so in the last part of lecture 12, the controller we designed was really quite kind of simple. All it was is a gain term, remember? And let's remember why that's a good thing. And hopefully this picture will show you what I wish to convey is the following. Suppose I give you a transfer function for the plant, okay? Remember, we obtain the benefits of feedback when we make the loop gain large. Large meaning much greater than 1, okay? So the way proportional feedback does that for you is that, okay, if you recall the loop gain, which is given by the product of the plant transfer function and the controller, which for the proportional case was just a gain here, okay? The effect of the controller is simply to slide the loop gain up, okay? This way. This is 1 here, okay? So if you make the loop gain move up in this way, then you will obtain the benefits of feedback, okay, over you will obtain benefits of feedback over a wide range of frequencies, okay? Okay. So when we did this, we found the following. We found a reduction in the tracking error, okay? We found a reduction in the sensitivity to the plant variations, and we found a reduction, in the effect of the disturbances on the output, okay? All of these with respect to the equivalent open loop system that he introduced, okay? But notice this is reduction, not elimination, okay? Certainly if we could eliminate all these things for all frequencies and so forth, we'd have an optimal controller, which we can't make, okay? But perhaps we want to say, how about if I can make the controller such that the system really behaves close to perfection, okay, at the frequencies that I really care about. And it turns out for many, many applications, the frequencies you absolutely care about are the low frequencies, DC, okay? In the cruise control, for instance, the cruise control for a car, if I want to make my car go steadily at 5 miles an hour, okay? I mean, no, 5, that's too little. 25, let's say. Even more, 40, okay? Let's say you're at 40 miles an hour. I don't have a car, so that's all these. Okay, so you want to cruise at 40 miles an hour, okay? So if you have proportional control and you command 40 miles an hour, if the person who designed the controller was good, they would give you the proper 40 miles an hour at the, at say when the ground is steady, okay? But suppose now you start going up a hill. Okay, with proportional control, what you're going to find is you won't go at 40 miles an hour. You'll go possibly maybe at 38, depending on the details. Okay, but you won't using proportional control. You won't stay at 40 miles an hour as you slope up. Okay, the reason being that the sensitivity at DC, okay, despite being small, is not 0. For proportional control. In other words, when you look at the product of PC, okay, in the low frequency limit, it's not infinity. It may be large, but it's not infinite, okay? So The next type of controller architecture that we're going to study solves that problem. Okay? It makes for really good controllers at low frequencies. Okay? And so the idea behind that is what we know as proportional integral control. So to motivate that, we go back to the page. Okay. So, like I said before, for proportional control, the DC sensitivity is given by this. And it may be large, but it's not small. Sorry, it may be small, but it's not 0. Okay? Okay. So, to make the sensitivity at DC small, of course, what we can do is make the controller gain very large at DC. Okay? And how do you make a controller gain be very large at DC? And here's the intuition. Maybe I can put a pole at the origin for C. Okay? This would make your sensitivity exactly 0 at DC because this term is infinite. Okay? So if you could achieve that, you would have perfect DC tracking, okay, for a constant input. In other words, if I input a step of 1 here, asymptotically, you will get 1 at the output. Okay? Okay, that's another thing. And since the sensitivity at DC is 0, you also find that the plant here may have variations in DC gain, but that doesn't matter, okay? You will still have perfect tracking, okay? In other words, no change in the transfer function at DC despite those plant variations, okay? Okay. So the question is this possible? Could it ever work? And the answer is, why could it not work? Why would you be suspicious that it may not work? The answer is, you've put a pole now at the origin, okay? So under feedback, remember from what we've been talking about before, your poles will move. So if you put an a pole right at the origin, it's extremely tempting for that pole to move into the right-hand plane and cause your system to be unstable, correct? That's the intuition. You can also think about it in this way. When you put a pole at the origin, okay, you're effectively adding some kind of delay to the system. And so delay in the context of feedback, remember Boyd developed this intuition later, in previous lectures, can very easily lead you into instability, okay? Okay, so I want to use a okay, and then one of my notes here. Okay, so here's the controller architecture that we're going to study now. It consists simply of a proportional gain term and an integrator term, okay? And these two terms here are given the names of proportional gain here and integrator gain, or integral gain, okay? So I don't like seeing this so much. I prefer to rewrite this in this form. For me, it makes more sense because I can see the 0 and the pole and the DC and the high frequency gain, okay, right away. Okay, so I choose to rewrite this in this form. That helps me understand what's going on more. Okay, so here's the catch. Here's the controller we've made. We've put a pole at the origin, right? So the effect of that is to give you an infinite gain at DC. Remember, on a logarithmic scale, this point never corresponds to 0 frequency. It may correspond to small frequency, but it's never 0. 0 is off on negative infinity, okay, in this scale. So the transfer function rolls off from plus infinity, okay, at minus 20 dB per decade, okay, until you reach this frequency, k sub I over k sub p, the ratio of the controller gains, okay, where you find a 0, which eventually cancels that roll-off and gives you a steady magnitude from frequencies above that, okay? The high frequency limit is exactly kp for the magnitude, okay? So this shows clearly what the effect of adding the integral term is. It gives you extremely high loop gain, okay, infinite loop gain at DC, and very high for low frequencies, until all of a sudden the pole kicks in, and then for higher frequencies, you're just left with the constant contribution of the controller, just like you had in the controller, in the proportional control case. Okay? Okay. Okay, so hopefully this plot helps. Okay, so like I said, you'll see this is widely used in practice. We've gone over these definitions, and if you look in the time domain, what happens? Okay, if you want to look at it from this perspective, it's simple. The control effort that you apply to the plant, okay, has two terms. One, which is a corrective term, it's proportional to the error. This is what we had from lecture 12, the proportional control term. And this other term, okay, this term here is proportional not to the error, but to the integral of that error, okay? And so a constant error E, you find, yields a constant corrective reaction from the controller, from the proportional controller part, okay? And it gives you a growing corrective reaction for the from the integral part, okay? And so what that means is the controller with integral action, okay, is mean, if you want to think of it that way. If I say the proportional controller says the following: I want 10 at the output, and then what comes out is 8. Say, okay, that's good enough. I'm okay. Okay? But when you have integral action, you do the following. I command 10, okay? Say I get 8 out, okay? Then I give you a correction, okay? Which, okay, the proportional controller will also give you. I give you a correction. But if the system doesn't respond to that correction, it gets really mean. So now instead of adding a small correction, it'll make that correction increase until it sees the system doing something. So it keeps penalizing you more and more and more as the longer you take to get to the desired point. Okay? All right. So is everybody clear why we call this PI? PI means for PI stands proportional plus integral control. Okay? Whoa. Okay. So I'm going to go into this one last example before we jump into the quiz. Okay? Okay. So to go back to the heating example, okay, we're adding now, go back to the heating example with a specific kind of controller, okay? I'm not telling you how we chose the 1 for the proportional gain and 2 for the integral gain. But suppose we're given this, okay? And so if you write it out, you realize you have a 0 at -2 and a pole at the origin, like we said before. Okay? Okay. So in this small drawing, very small drawing, okay, I show here the I show the open loop poles right here from the plant, and I show additionally the pole and the 0 contributed by the controller. Okay, and the interesting thing is that once you close the loop, okay, you find that the poles moves a little bit. Okay, this one moves in this direction to -12.2. Okay, and these ones, they join and they split similarly to before. Okay, and they're now at this frequency. Okay, this one, and finally, the pole that we have at the origin moves toward the 0. Okay, and eventually, at the choice of controller parameters we have, it's at -1.51 radians per second. Okay, so to show the effect of that, last thing. Okay, let's compare. This here is a step response to a disturbance input. Okay. Yeah. So if I input a unit disturbance to the heater right here. Okay, and there's more stuff around. Okay, if I input a unit disturbance here, Okay, this is what I find for my error in the open loop case. I have a steady state error of 1. Okay, so with proportional gain alone, from last chapter, we found this kind of response, step response to input disturbance error. Notice that while the steady state error is smaller than the open loop case, it's not 0. Okay? And with the proportional plus integral term here, from this example right now, you find that that indeed you get the desired steady state response of 0 to this disturbance when you use the proportional plus integral controller. Okay? So, okay, this is an exciting topic, and we're gonna finish up this class next time, and I think it's time we go to our quiz. Jessica.